Okay, I might get started. Hello, I'm Liam Wright. I'm a lecturer at the Centre for Longitudinal Studies at University College London. And today, I and two of my colleagues are going to be talking about methods for handling mode effects. And this is part of some work that we've been doing as part of the Survey Futures project, which is funded by the ESRC. So the presenters today are me and Georgia Tomova and Richard Silverwood, who are both at UCL and at CLS as well. Okay, I'm going to start with some background, then I'll give an outline to the rest of the webinar. So surveys are a type of self-reported data that are collected directly from respondents. Surveys are carried out in a mode, and there are several different modes that can be used to collect survey data. So there might be interviewer-led modes like face-to-face in-person interviews, telephone interviews, or more recently, video interviews over Teams or Zoom. And then there's also self-complete surveys like paper or web questionnaire. Surveys can use a mixture of modes within a given data collection. And many surveys have started to use mixed mode designs in their surveys to reduce costs or increase response rates. So one popular design that's been increasingly used is a sequential mixed mode design. So for instance, you might invite participants to respond by web questionnaire because that's cheapest and most convenient. And if they don't respond, call them up for a telephone interview or knock on their door for an in-person interview to increase those response rates while reducing overall costs. If you've got a longitudinal study, there's another aspect in which mixing of modes can be occur as well, and that's where you mix the modes between survey sweeps or between survey waves. So particularly for older longitudinal studies, for technological reasons, they might have started out with face-to-face interview for the first, say, 30 years or so of life, and then more recently incorporated different forms of data collection like a telephone interview or web questionnaire. So you'll have people in one sweep responding by face-to-face interview, and later on different modes will be used. Now, although many things are done by survey designers to try and reduce the differences between modes, there are some inherent differences between the modes that distinguish them. So the key one is the presence of an interviewer. In interviewer-led modes, you have a physically, or at least you're speaking to an interviewer, they read out the questions, deliver them to you, and you give the response back to them, versus self-complete ones where there's no interviewer present. And that might affect the answers you give, because for questions where there's some social desirability concerns, you might be unwilling to answer that question, get it to the response to the interviewer, or you might give it a different answer. Interviewers can also provide some motivation. If it's a web questionnaire, you might just fill out a survey haphazardly, whereas an interviewer will be able to give you some motivation to do it more thoroughly and accurately, and they can provide instruction as well on particularly difficult questions. There's also some inherent differences in how questions are presented. The main difference is whether you have a visual presentation, so you read out the questions, or oral presentation where the interviewer will say the question out loud and you'll respond. So this can lead to something called primacy and recency effects, where if you're reading the question, you might only look at the first response categories for an item, whereas if you're hearing them, you might remember the ones later in the response categories that you can give. There's also differences in the context of response too. So an interviewer will typically, face-to-face interview might occur during working hours, whereas a web questionnaire can be answered anywhere at any time, even during the night. And that could obviously affect responses too. So these differences might affect how people respond to the same survey item. And differences in response between modes due to how the items are measured are termed mode effects. And that's what we're speaking about today. So mode effects can manifest in a number of different ways. One can be differences in item response. So if you've got a interviewer asking you a question on a particularly sensitive subject, you might refuse to answer that question at all, whereas you might have answered it in web. might also affect that the response you give conditional on given a response as well. So if you have an interviewer and it's a particularly sensitive question, you might say that you have better mental health than is actually the case, whereas you might answer more accurately in a web mode. And finally, there's more aggregate phenomena too, where you can see something over multiple items, so something like straight lining. So on screen, I've shown a table that's the 6 items of the CASP-6 measure of quality of life. If you, in a web questionnaire, this would be printed out on screen and you would see it in a response grid, and straight lining behavior would just be to give the same response to each item, so a straight line down the grid. And that might be due to lack of motivation and interest in thinking about the questions thoroughly. Georgia, who's one of the presenters in this talk, has given she recently finished a systematic review looking at all the different mode effect experiments that have been conducted looking at mode effects on item means, and there's some stellar work. There was 90 different studies and done stellar work summarizing the headline findings from all that disparate information. So a few of the headline findings are that mode effects exist, but not always. And when they do exist, the effect sizes rarely exceed something like 0.3 standard deviations. So using Cohen's rule of thumbs for Cohen's D, that would be a small effect size. One of the key situations in which a mode effect might occur is where you're comparing anonymous and non-anonymous modes, particularly for sensitive questions. So for instance, questions on mental health in a face-to-face survey versus a web questionnaire. Now, surveys that are asking face-to-face surveys, in-person interviewer-led surveys that are asking sensitive questions often have a self-complete section, but even the physical presence of an interviewer alone can sometimes lead to mode effects, even in self-complete. Excuse me. So why is that a problem? Well, systematic differences between how people respond in different modes can lead to bias in analyses. Most obviously, this can occur for univariate descriptives. So on screen, I have a plot from Ben Domingue and colleagues, an analysis that they did of mixed mode elements within the US health and retirement study, which is a longitudinal study of aging. In this survey, in 2-year intervals, respondents were asked to complete a measure of cognitive functioning. And on screen is just the average score on that across the population on that variable at different time points and in different modes. Now, given this is an aging population, you would expect that cognitive functioning would decline over time. But actually, what you see on screen is that because different modes are used, between some time points, the scores on cognitive functioning actually increase. So for instance, in the telephone versus the face-to-face mode, you have higher cognitive scores, even though telephone came after face-to-face mode, and particularly in web versus face-to-face mode, you get higher cognitive functioning scores. So if you didn't think about the design of the survey and you just looked at the variables, the data as it was, you might think that cognitive functioning was increasing over time, when in fact this was just reflecting the survey design. So that's univariate descriptives, but there's also problems when you look at associations between variables. So on screen, I've got simulated data for 2 variables, financial security and quality of life. Because I've simulated the data, I've imagined that there's no association between these 2 variables. However, excuse me, for each of them, I've assumed that they're collected in a mixed mode survey, web or telephone, and that there is a mode effect so that people report higher financial security and higher quality of life in the telephone survey versus web, because the telephone is not anonymous, whereas the web one is. So you might be less willing to say you have poor quality of life or low financial security to an interviewer compared to anonymously. So what you find is a positive association between these two, as shown by the red regression line just overlaid over the individual points on the scatter plot. But if you actually looked within a specific mode, for instance, now I'm just highlighting the data points from the web mode and reran a regression, you'd find no association, which is the true association between these variables as simulated rather than just reflecting the survey design. So having two variables that both are subject to mode effects can cause an association between those variables that's spurious rather than reflecting the underlying reality. Now, mode effects aren't the only reason why you might get differences between responses between modes. It can also occur because of something called mode selection, which is differences in responses between modes due to who is responding rather than how they are being measured. So people are rarely randomized in surveys to different modes. There's usually differences in the characteristics between different modes of the people. So this can be because of differences in coverage. For instance, a survey might not have a telephone number for some individuals and so might only invite them via web. Could be differences in preference. People might be pushed to use a web survey, but offered the chance to request a paper questionnaire instead if they want it. So for instance, older people might use that paper questionnaire when provided. And then it can also happen implicitly because of other aspects of the survey design. So for instance, in the sequential mixed mode design, where if you don't respond immediately, you are then invited by another mode. If you just happen to be someone who requires multiple invitations before you respond, then you will appear in the later mode rather than the early ones, regardless of the fact of it being a different mode. It's just the difference of the mode over time. And if that's related to other factors, then that'll be related to mode selection. So it's not just the combination of mode effects that can induce bias in associations, but also combinations of mode effects and mode selection. So now on screen, I've got another data simulation to make this point. So here we have two variables, computer skills and quality of life, in a scatter plot with computer skills on the x-axis and quality of life on the y-axis. I've assumed that computer skills aren't subject to a mode effect, that regardless of whether you're interviewed by web or telephone, you would give the same response. But computer skills might be related to the preference that someone has for a particular mode. So for instance, if you have higher than average computer skills, you might respond by web rather than telephone. Then we also have quality of life, which isn't subject to mode selection, but is subject to a mode effect. So people in the telephone mode, because it's non-anonymous, might report higher quality of life than they would have done if they're in the web mode. If we then run a regression line between the data points, keeping people in the mixed mode data, data from both modes, you see a negative association. And that's because people with low computer skills were more likely to be in the telephone mode and more likely to report high quality of life because of being in that mode. If we just looked at a specific mode here, web, we've just highlighted the data points for web and ran the regression line, would find no association again. So this would find the underlying true effect rather than the one that was spuriously created by the survey design. So at this point, you might think, well, why don't we just condition on mode, look at data from one mode rather than both modes? But if you have mode selection on two variables, then this can also create bias. The conditioning on mode can create bias. So here we have a scatter plot for computer skills and number of children. If you have a high number of children, then you might be more willing to use the web mode because it's more convenient. And if you have high computer skills, you might be more likely to use web rather than telephone. If we run the regression line through all of the data points, because these are only subject to mode selection and not mode effects, you find no association whatsoever. But if you condition, say stratify and just look at the data points from the web mode, you actually end up finding a inverse association between the two variables. And that's because if you know someone responded by web and they have low computer skills, then they must have a large number of children to want to use web. So you've got an inverse association between the two. Now, this can be quite counterintuitive. And so in the next part of the talk, George is going to talk about using something called causal directed acyclic graphs to conceptualize mode effects and work out how bias can arise from them in different types of analysis. Because that material might be particularly new to people, after her 35 minutes that she's going to talk on that, we'll then have a Q&A for 5 minutes just on that material. Following that, we'll have 20 minutes from Richard on standard methods that are proposed for handling mode effects and why they might not work in practice, particularly because of this problem of mode selection. And then I'm going to talk about another approach that might be more promising. So this is quantitative bias analysis. We've tried to keep this the instructed taught elements of this webinar relatively brief relative to the 2 hours that we've got allotted. So at the end, we've got a 25-minute section for the Q&A. So over to Georgia.
So thanks, Liam. So Liam has already given a great introduction to what mode effects and mode selection are and some of the possible implications of this. And what I'm going to do in this section is try and use DAGs to conceptualize mode effects and hopefully help you understand in a more intuitive way some of the potential implications and also the implications of not recognizing some the downsides of using some approaches to handling mode effects. And I know that some of you here will already be familiar with DAGs, whereas for others, that might not be the case. So just so that we're all on the same page, I'm going to give a brief introduction on DAGs. And then for those of you who are already familiar with them, hopefully this will be a useful recap. So DAGs, which is short for directed acyclic graphs, are a type of causal diagram or a type of graph that, as the figure on this slide shows, the representation of the hypothesized causal relationships that we believe exist between variables. For example, in this figure, we have a collection of different variables that are represented by these squares. And that are all connected by a set of different arrows that indicate these causal relationships. And DAGs are extremely useful for both applied and methodological research. In terms of applied research, the main way in which they're used is to try and guide us towards selecting an appropriate set of variables to control for. The reason why we need to do this is suppose we have experimental data, so we have some data from a trial. Because of the randomization, we know that the groups that we're comparing have the same probability of the outcome at baseline, and that's why they are comparable. Obviously, in observational data, this is not the case because we don't generally analyze exposures that have been randomized, but we still want to make these groups comparable. And one way to try and do this is to achieve this via statistical control, for example, by adjusting for confounders, by adding them as covariates in a regression model. And what DAGs help us with is to select the most appropriate set of these covariates to control for, and also avoid variables that we shouldn't be controlling for. So in practice, this is how DAGs are most commonly used for applied research. But they are also extremely useful for methodological research and for understanding different methodological issues and concepts that might be much more difficult to understand without having a sort of graphical representation. For example, although we knew about selection bias before, DAGs were really mainstream, being able to depict different types of selection bias with DAGs have really significantly improved our understanding of all the possible implications. And DAGs have also helped uncover a lot of apparent paradoxes like the birth weight paradox. And that's also how we're going to use DAGs in this section to try and understand conceptually the problem of mode effects and mode selection. So as I mentioned, DAGs are graphical representations of causal relationships between variables, where each of the variables we consider, for example, in this figure, we have 6 variables that are called A, B, C, D, E, and F. These are represented by what we call nodes. And then the causal effects that we hypothesize exist between them are represented as arcs or arrows. DAGs are called directed because the arrows or the arcs explicitly depict the direction of the causal effect from one variable to another over time. And they're acyclic because there can be no circular paths, meaning that we cannot start from one variable, follow the arrows, and then arrive at the same variable. Importantly about DAGs is that they're non-parametric, which means that the arcs between two variables do not say anything about the strength of the effect, the direction in terms of sign, or the shape of the relationship. It only indicates presence or absence of assumed causal effect between the two variables. And DAGs are also probabilistic. For example, when we place an arc from A to C, we say that A changes the probability of C. But importantly, A is not necessary or sufficient for C. What that means is rather than A and C, we have smoking and lung cancer, and we place an arc between them. We say that smoking changes the probability of lung cancer, but it's not necessary for it, meaning that lung cancer can occur without smoking, and it's not sufficient for it, meaning that just because we observe smoking, just because someone smoked, doesn't mean that they will get lung cancer. So these relationships that we depict are probabilistic. And a collection of arrows or arcs is called a path. So whenever we have two variables that are connected by one or more arcs, we have a path, and this is regardless of the direction. For example, in this figure, variables A, C, and F are connected via arrows that all run in the same direction from A to C to F. This is one path. But we also have a path from D to F to E, even though it's in different directions. So we have D causing F and then going backwards to E. And when paths are open, and we'll see what that means in a few more slides, they transmit associations or dependencies between the variables that are on this path. And when paths are closed, they do not. When we have a collection of arrows that all run in the same direction, we call this path a causal path or a directed path. For example, in the figure here, we have a path where A causes C, which causes D, which causes F. So with the path from A all the way to F, all the arrows run in the same direction, so we call this a causal or a directed path. And this path can be closed by conditioning on a variable on that path. What that means is we control for it in some way. For example, we adjust for it in the regression, or we stratify by these variables, or any form of conditioning. For example, if we were to condition on C, which is the second variable on this path, we will close the path. And so, for example, changing A, the effect of A will not be transmitted further on this path onwards to F. So it will stop at C. With some additional notation borrowed from other types of graphs, we can also use DAGs to depict measurement error, which will be very relevant for mode effects. So we do this by depicting the latent version of a variable, which is the underlying true version that is unobservable directly using circles or ellipses. And we depict the observed version of the variable using squares. For example, in this figure here, we have a collection of variables that all cause the outcome y. And this outcome is a latent variable, which is unobserved. However, we have a measure of it, y star, which is depicted as a square. And we consider that y star is caused by y. And when we depict different causal relationships, when you have latent variables, we always believe that they're operating on the latent level. So A, B, and C all cause the latent y. So they cause the true y. But we use the measured y star in the analysis because this is what we can measure. So how can we then use this to understand mode effects? So first we need to see how we would depict mode effects using this notation in DAGs. We can understand mode effects as a form of systematic measurement error. So suppose we are interested in some measure of smoking. So we have the smoking variable, and the measured version of it, we would call S star, is depicted in a square. Obviously, this S star will reflect the underlying latent smoking, which we depict in S in a circle. But if we have measured smoking using more than one mode, and smoking was reported differently in the two modes, then we might also have a mode effect. So in addition to the underlying true smoking, some of the variation in the observed smoking or S star will be due to the mode. So we also depict mode as M in this square, and we depict it as another cause of S star. And we're going to use the concept in this structure throughout to see the implications in different contexts. So suppose now this smoking variable that we've considered is an outcome in some illustrative analysis that we're interested in. Suppose we're interested in the effect of occupation on smoking, so we would call this X and Y, the exposure and the outcome. So suppose here that the mode effect only exists on the outcome, so we have the path that we're interested in, the relationship is between X and Y. However, Y is unobserved. The true Y is unobserved, so it's depicted in this circle. And instead, we have the Y star, which is also subject to a mode effect. So M is an additional cause of Y star. Now, what this might lead to in a potential analysis is that, so on average, this would not bias the association, but it might introduce error. And for this reason, actually, variables like M that only cause the outcome are often called precision variables because they have implications for precision. But the solution to this is very simple. And by controlling for mode, or conditioning on mode, we can resolve this and remove the error that would have been introduced otherwise. Of course, we can have the situation that's the other way around. So smoking is the exposure, not the outcome in some example analysis. For example, if we're interested in the effect of smoking or X on stroke Y, we might assume that stroke will be measured objectively across modes, but we know that smoking will be subject to a mode effect. So we use the same structure this time in the exposure. So when the exposure is subject to a mode effect, this can actually introduce bias in the observed association between X and Y. And typically, this will be in the form of dilution, which means that typically the bias will attenuate the observed estimate towards the null. However, the solution to this is the same, and if we can condition on mode or control for mode, we can resolve this. So regardless of whether we have a mode effect on the exposure or the outcome, the solution is the same. Of course, you might already be thinking that mode effects might exist on both the exposure and the outcome. For example, if we're looking at anxiety and smoking. So what this would introduce is a type of measurement error that we call dependent measurement error, and in this case, it's dependent on mode. We can also conceptualize mode in this case as a source of confounding. And I'm briefly going to introduce how confounding can be best understood and depicted in DAGs. So we said that the collection of arrows or a path where all arrows run in the same direction is known as a causal path or directed path. So confounding is one type of a non-causal path. So a confounding path is also known as a backdoor path. For example, here we have a figure in which we focus on the variables C, B, and F. So this is a path that does not go in the same direction. So first, we go backwards from C to B. So backwards in the direction of the arrow, and then onwards from B to F. In other words, B is a common cause of C and F. What this would introduce is a non-causal or spurious association between C and F that is due to B being a common cause. In other words, we would call B a confounder. So they would confound the observed association between C and F. But confounding paths can also be closed by blocking the path or conditioning on the variable. So if we condition on B, we would close this confounding path, and the confounding that's introduced between C and F will be removed. Like one of the classic examples to try and understand confounding more intuitively in DAGs is that suppose we collect some observational data, we might observe that ice cream consumption is associated with the incidence of shark attacks. So we depict in the figure ice cream as X, this is the exposure, and then the incidence of shark attacks as Y. And we know that this is because weather is a common cause of both consuming more ice cream and potentially going into the ocean and exposing ourselves to sharks. So in other words, weather is a confounder for the relationship between ice cream and shark attacks. And so we can depict C as a common cause of X and Y. And if we were to control for C, we would close the confounding path and we would expect this relationship to disappear. Now let's try and apply this to the context of mode effects. So suppose we have this example where we're interested in the effect of anxiety on smoking. So the way we would depict it here, one possible way would be to depict both the latent X and Y, so the latent anxiety and smoking. And really what we want to know is the arrow that goes from X to Y. So here we assume that X causes Y and we want to estimate this path. However, we don't have the latent X and Y. Instead, we have some measured versions of them, which we call X star and Y star. Obviously, X will cause X star and Y will cause Y star. But both of these might be subject to mode effects. In other words, their observed association might be confounded by mode, because the way we would depict this is we have mode, which is a cause of both X star and Y star, if we believe that they're subject to mode effects. So we can immediately see this confounding structure. And of course, it works in the exact same way. In this case, if we were to control for mode, we would close this confounding path and we would remove the confounding that would have been introduced by mode. However, as Liam mentioned, mode effects is not the only thing to worry about. And we should also consider mode selection. So as a reminder, mode effects refer to how people respond. And these are different to mode selection, which refers to who responds by each mode. And Liam already mentioned that there are various different causes of mode selection. And in general, we understand mode selection as potentially being affected by a variety of different factors, or a variety of different variables that might be relevant in our analysis, which might include the latent exposure and outcome themselves. So mode selection, as hopefully you'll be convinced by the end of this, must be considered very carefully before deciding to control for mode, because in a lot of these examples that we've seen, the solution to control for mode is very simple and it works in all of these scenarios, but mode selection adds an additional complexity. And to understand it, I will introduce a different type of non-causal path, which we can refer to as a collider path. So like confounding, this is another type of non-causal path, meaning that the arrows don't go in the same direction. For example, in the figure here, one type of such collider path is the path from D to E to F to E. So D causes F, and E causes F. In other words, the path goes from D to F forwards and then backwards from F to E. In this context, we would call F a collider because the paths from D and F collide in, from D and E collide in F. So F is a collider variable. Now, just by existence, collider paths are closed. And whenever we have a collider path, just by existence, it does not automatically introduce any bias. However, it is possible to open a collider path and introduce bias. So this would happen if we were to condition or control for this collider F. If we condition on F, this will open the path from D to F to E that was previously closed, and introduce a spurious association or dependency between the common causes of F, which are D and E. So D and E will be associated in a spurious way due to F being conditioned on. And so this type of spurious association that is introduced is known as collider bias. And I'm going to use one of the classic teaching examples for understanding collider bias, which is the following. Suppose there may be two reasons why someone might become a Hollywood star. They are either very good at acting or they're very good looking. So we can depict this in a DAG in this way. So we have the acting variable, which causes being a Hollywood star. And we also have the physical appearance variable, which also causes being a Hollywood star. Now, in the general population, we shouldn't expect that acting ability and physical appearance are necessarily related, directly related causally. However, if we were to look within a sample of Hollywood stars, we might see an inverse association appear between them. And this is because once we look within people who are already Hollywood actors, we can understand this as a type of conditioning. We are looking at a restricted sample, so everyone there has the same value of Hollywood actor being, for example, 1 in a binary variable. So this is a type of conditioning. So once we condition on this collider, there will appear to be a negative association between the two reasons for being a Hollywood actor, the acting or appearance. And this is because if we know that someone is a Hollywood star, but they're not very good at acting, then they must be very good looking to have made it. And the other way around, if they're not very good looking, then they must have exceptional acting ability. Of course, they can be both, but the point is they cannot be neither. And so we see this conditional dependency between the two. And although this is a toy example, collider bias can sometimes be a bit more difficult to understand or see. And so I'll try and give you another slightly more complex example just so that you understand the implications of this in practice. So some of you here might have heard of what's known as the obesity paradox. The obesity paradox refers to the finding that obesity is observed to result in lower mortality among people with chronic conditions. Obviously, this is quite counterintuitive because we would imagine that on top of having a chronic condition, having obesity as well would be expected to result in higher estimated mortality. And so that's why there is this paradoxical finding. Now, the obesity paradox is a combination of several different biases, but one of them is collider bias. The reason why it occurs is that this is always observed in people with chronic conditions. For example, this might be if we study a sample of people who have experienced a heart attack. We can understand this as conditioning on heart attack because everyone in the sample has had a heart attack. And then obesity is one potential cause of a heart attack, and we're interested in the effect of obesity on mortality. So here in this figure, we have obesity causing a heart attack, obesity causing mortality, and heart attack causing mortality as well. So what we might not realize is that there will exist many other causes or many other reasons of being in the sample, which are other causes of having a heart attack. Now, many of these we might know, but many of them we might not have measured, and also many of them we might not even know about. So once we look within this restricted sample that is conditional on having a heart attack, we introduce a spurious association or a conditional dependency between the different causes of having a heart attack. For example, in this case, obesity and all the other causes. So the reason why this might result in obesity appearing protective is that although both obesity and other causes might increase the risk of a heart attack and might increase the risk of mortality, it is possible that some or many of these other causes have stronger effects on mortality, which, because of the conditional dependency introduced, might make obesity appear protective, because we can understand this as estimating the effect of obesity instead of all the other causes. So sometimes this can result in really paradoxical findings, like once we try to depict in a DAG, it's much easier to understand. So now let's return to the context of mode selection. Suppose we have some example where we're interested in studying the effect of years of education on the frequency of internet use. So both of these we might expect to be related to participation via a certain mode as opposed to another. So the way we can depict it in the DAG is that the latent X and Y are both causes of M. And of course, once again, we have the measured version X star and Y star. For the purpose of this example, we just focus on mode selection. And so we assume here that M is not a cause of these measured versions. So we assume no mode effects. However, if we are used to always controlling for mode when we're working with mixed mode data, because we know that this is something that we need to be controlling for, this is where we can start running into problems. Because mode is now a common consequence of the latent X and Y, we can hopefully immediately see that this represents a collider structure, and so mode is a collider. If we were to naively control for mode in an example like this, then this would introduce collider bias into the relationship between X and Y that we estimate. Of course, there can be both mode effects and mode selection. Suppose we're interested in the effects of depression on alcohol intake, so we depict depression with X and alcohol intake with Y. Here, both are likely subject to mode effects and probably both a source of mode selection. So we draw the DAG in the following way. We have the latent X and Y variables that both cause M, which is mode. In turn, mode causes their measured versions X star and Y star because we have mode effects. In this situation, if we were to control for mode, we would resolve one problem, which is the confounding that mode introduces. We might introduce another, which is that it might also introduce collider bias. And sometimes this might not be immediately obvious. For example, if we were to replace the outcome rather than alcohol intake, we look at something like fruits and vegetables intake because we're interested in studying the effect of depression on, for example, healthy diet. Here, although both of them would likely be subject to mode effects, so we would still consider that M causes X star and M causes Y star. And we have the same exposure depression, so we know that this might be a source of mode selection. Fruit and vegetable intake is very unlikely to cause mode selection, so we wouldn't draw an arc from the latent Y to M. And so because we don't have this immediate collider structure, we might think that it's safe to simply condition on mode because we have mode as a confounder, but mode here is not a collider. Except there might be other variables like the latent U, which might be causes of both mode and the latent fruit and vegetable intake. Now, unfortunately, collider bias can also be introduced in this structure as well. And if we were to control for mode here, we would still introduce a spurious association between X and Y via the unobserved U. Now, if U is a variable that we can observe and that we have measured well, we can reduce or we can correct for the collider bias that is introduced. But the point is that there will likely exist a lot of different U's that we might not have measured or that might be completely unknown. And I'll just make a quick point on longitudinal analysis. So this DAG is not meant to put you off. It's just to show you that things in practice can get a lot more complex. So suppose we are interested in the effect of depression on alcohol intake over time. So we have different measurements of depression and different measurements of alcohol intake over time. What we have in this case, in this example here, is that we might also have mode changing over time. So we might have different instances of the mode variable. And so in this figure, we have depression at 2 time points, alcohol at 2 time points, and mode at 2 time points, in addition to both the latent and the observed depression and alcohol variables. And we can see that most of these variables are causally related in some way. Although this might appear much more difficult to figure out, we can use the exact same principles that I've introduced so far to try and figure out what to do. And there isn't really one general solution. It always depends on what the research question is. So you always start with trying to figure out the exact research question, which are the 2 variables that you're interested in. This will then help determine the most appropriate action. What needs controlling for? How does mode exactly relate to the specific 2 variables that we're interested in? Is there any risk of collider bias? Are there any risks that we can, any problems that we can run into if we decide to control for mode? In most cases, it's just good to be aware that conditioning on mode might lead to collider bias, while not conditioning might lead to confounding bias, because obviously reality is quite complex. And so hopefully this will, so I think this points to the fact that we need other potential strategies of handling mode effects, and this is what the next 2 sections will be about. So just to summarize everything I've said so far before we move on, the presence of mode effects and mode selections and mode selection in different examples will be very context specific. So sometimes mode will introduce mode effects in one variable or both the exposure and the outcome. So the similar for mode selection. So the way this behaves will be context dependent. Where we think that our variables of interest are subject to mode effects, but we think it's plausible to assume that there is no relevant mode selection, then the consequences of mode effects can be reduced by simply controlling for mode in our analysis. But in the presence of mode selection, controlling for mode risks introducing collider bias. And it's very difficult to predict how much bias that would be. This would also vary depending on scenarios. But sometimes it might be more than we've reduced by controlling for mode. And this also necessitates different approaches to handling mode effects than simply just controlling for mode in a regression. And hopefully you've been convinced that DAGs are very helpful tools for reasoning about this and to trying to understand the best possible strategy and how exactly mode effects and mode selection might impact your substantive analysis. And hopefully you've also been convinced that DAGs are just very useful in general. And now it's time for the next section.
Hopefully you can now see my slides. So thank you very much. Great to see so much interest in this important area of work. I'm going to talk now about a couple of the different sort of standard methods that have been used in the handling of mode effects. I'll go through some toy examples, looking at how you would apply them in practice, and then discuss some of the advantages and disadvantages of each. The first part, I think I can go through quite quickly because it is largely some duplication from what George has been saying already. Certainly some of the DAGs should be very familiar to you already. So it may be possible, as we've been hearing already, to account for mode effects using control variables. And the situation I'm going to be considering over the next few slides is where we're looking to obtain an estimate of the effect of some exposure, which I'll label X, on some outcome that I'll label Y. So in the very simple settings where there's no relevant mode selection, this could simply involve adding an indicator variable for mode to the substantive model. So some control for it, conditioning, including it in the regression model, or alternatively stratifying by mode, so analyzing within each mode. So let's look at this very simple example DAG here. So this is a DAG with 4 variables displayed as 4 nodes in the DAG. So X is our exposure of interest, Y is our outcome of interest that we don't observe directly. Instead, we observe an error-prone version of Y star, that's subject to mode effects, which are signified by the arc going from M to Y. And the arc from our exposure X into M signifies that there's selection into mode on the basis of X. So we're interested here in the causal effect of X on Y. And we can see through the absence of an arc from X to Y that there's in fact no causal effect of X on Y here. So when we conduct our analysis, we would hope to observe or to obtain a null estimate. So we've got our observed Y star here. We might start by fitting a regression model of Y star on X. Here, because of this open path from X via M to Y, we wouldn't obtain, through fitting a regression of Y star on X, the null estimate that we would expect. We would be picking up this spurious association between X and Y due to M. In this simple situation here, we can overcome this by controlling for M. So if instead we fit a regression model of Y star on X and include the variable M, it will block the open path from X to Y star via M, and we will appropriately obtain a null estimate. So if there's mode selection instead, according to some relevant variable, then accounting for mode alone might no longer be sufficient, and as George has already suggested, could even increase bias. And in this sort of example, we may consider additional control variables in our analysis. So in the second example, we've extended this simple DAG slightly by the inclusion of an additional variable, a measured variable U, which is a common cause of M and Y. So selection into mode is now on the basis of U in addition to X. So again, we're interested in estimating a causal effect of X on Y. If we start by thinking about fitting a regression of Y star on X, then we run into the same problem because we have an open path from X to Y star via M. We can solve this particular issue in exactly the same way by controlling for M. So perhaps including M in our regression model of Y star on X. But by doing so, in this example, we create an additional problem for ourselves. So here, M is a collider for U and X. And as George has already told us, if we condition on a collider, so here we condition on M, then we induce a spurious association between U and X. So we're opening up an additional path. So here that additional path is really from X to M to U to Y star. So controlling for M alone wouldn't give us an unbiased estimate of the causal effect of X on Y. In this example, we can additionally control for U. That will block that previously open path, and a regression of Y star on X, controlling for M and U, should achieve the anticipated null estimate for the effect of X on Y. But what if U is unobserved? Clearly then we can't control for it and we've got a problem. If we don't adjust for M or control for M, then we're picking up a spurious association via the mode. But doing so, we're opening up this additional spurious path, and therefore even in this toy example, it's impossible for us to unbiasedly estimate the effect that we're interested in. And as George has already said, it may be possible that the required set of control variables doesn't or couldn't exist at all. So for example, if if Y is both subject to mode effects and a source of mode selection. So example 3 is the same as the DAG for example 1, but we've now additionally added an arc from the unmeasured or latent version of Y in a circle to M. So this is signifying that mode selection is now on the basis of the latent Y as well as X. So again, here, if we fit a regression of Y star on X, then it would be biased initially because of this spurious path via mode. If we control for mode here, then now X and Y, M is a collider for X and Y. So when we control for M, we're inducing spurious association between X and Y and opening up this additional path between X and Y star. So from X to M to Y star. And here, clearly, because Y is unmeasured, we can't control for it. So again, we have a problem. So statistical control can be used in a slightly different context as well. So instead of trying to use this to unbiasedly estimate the effect of X on Y in this example that we're interested in, we can instead try and estimate the mode effect itself and use this to predict counterfactual values for the alternate mode. So let's say, for example, we're interested in analyzing some observed mental health data being collected in a mixed mode survey using web and telephone. We suspect that respondents under web will be giving us more truthful answers because it's an anonymous mode of data collection, whereas those responding by telephone, where there's an interviewer present, so non-anonymous, may not be so truthful. So we suspect there may be mode effects. If we can estimate that mode effect, then we can use that to correct the observed data that we have for those, in this example, in the telephone mode, and then analyze revise that corrected data set as if it had been observed, potentially bootstrapping the whole thing to appropriately incorporate uncertainty. So I'm going to go through the same 3 example DAGs here, but now instead of being interested in estimating the effect of X on Y, we're interested in estimating the mode effect. So that is this arc here that goes from M to Y star, the mode effect. So in this example 1, if we regress Y star on M, then this will give us an unbiased estimate of the mode effect because there are no spurious paths from M to Y. There are no backdoor or biasing paths from M to Y star. In the second example, where we extended the DAG by adding the node U, that's a common cause of M and Y, this is no longer the case. So our mode effect, our effect of M on Y star, is now biased by a confounding backdoor path via U. So this path from M to U to Y star. In this case, because U has been observed, we can control for U. So now regressing Y star on M, additionally including U in our model, would allow us to unbiasedly estimate the mode effect. However, if we again consider the case where U is unobserved, then we can't remove this confounding. So we would be unable to unbiasedly estimate the mode effect. And here, I should say, just to ensure that it's clear, it's a toy example, we've included a single variable U, but in reality, there would be a number of different U variables, perhaps some of them observed and some of them unobserved. So there would be a lot more additional complexity to consider. In the third example, where Y is also a source of mode selection, we can again consider estimating our mode effect by regressing Y star on M. But here, Y itself, the unmeasured version of Y in the circle, is a confounder for the mode effect. And so here we can see that because that's unmeasured, we can't control for it. So again, it's problematic in terms of estimating the mode effect to use in this sort of correction approach. So just to summarize some of these advantages and disadvantages of statistical control, very straightforward method, talking here about regression and other approaches that are within the conventional statistical toolbox, easily understood and implemented. The sorts of context that we work in, and I suspect many others will do, where we've got large general purpose social and health surveys, particularly longitudinal data, we've got very rich information. And so it may well be plausible, we can make a case that we have access to the required set of control variables, or at least something sufficiently approximating that. However, one major disadvantage here, perhaps the key disadvantage, is that it's an incredibly strong assumption that mode selection can be correctly accounted for. The required set of control variables may be unknown. We just don't know which variables we should be accounting for. We might know about them, but they've not been measured in this instance. So if it's a secondary data analysis, we've not been involved in the design and it's not been thought about, or they may be poorly measured, so themselves subject to measurement error, including potentially mode effects. And therefore, it's impossible to completely account for this bias. An additional consideration might be that when we adjust for causes of mode selection, we're then thinking about conditional estimates. So we might be changing the interpretation from what we would ideally be estimating. Okay, and then in this final part, I'm going to talk a bit about multiple imputation. So mode effects can be positioned within the framework of missing data, in that if we ideally would have observed everyone under one reference mode, then we can consider the information for the variables potentially subject to mode effects that were observed instead under an alternate mode as being missing in some sense. And that allows us to think about using methods that are originally designed for handling missing data to instead handle mode effects. So multiple imputation is one such method that's been used very widely over recent years due to its ease of implementation, particularly because it's well integrated into all major statistical software. So if we're trying to use multiple imputation to handle mode effects, what we would do is that we would consider, as I say, the values of variables that are considered to potentially exhibit mode effects. We would artificially set those to missing for individuals who were in fact observed under the alternate study modes. We would then develop predictive or imputation models based on the data from those in the reference survey mode, and use these predictive models to impute the information for these variables for those individuals who we in fact observed under the alternate study mode. So this would give us counterfactual values had we instead observed them under the reference mode. And I'll go through a toy example again of this in a minute, so it should become clearer. So these completed data sets can then be analyzed, used to provide descriptive statistics or estimating the associations or causal effects that we're interested in the usual way. But if we were just to go through this process and impute values once, analyze them as if they'd been observed, then this wouldn't fully incorporate the uncertainty that's due to the imputation procedure. So instead, multiple imputed data sets are generated using this approach. Within each imputed data set for a given variable, for a given individual, you're likely to see different values, a distribution of values across imputed data sets. Then each of these imputed data sets are analyzed using the substantive model, the analysis model of interest, and the estimates pooled using standard methods. Okay, so a toy example looking at this. Let's say that we're interested in analyzing a battery of mental health questions. So a number of questions were asked, and these were summarized into a sum score. And that's what we're going to be analyzing here. Questions were asked by two different modes. They were asked by web, which is anonymous, and again, we suspect people may be more truthful here. They were also asked by telephone with an interviewer present. And we suspect individuals may be less truthful in this instance. So there's a potential for mode effects. So the the table on this slide shows the first 5 rows, the data for the first 5 individuals in a hypothetical data set. So there's 3 variables here. The first is an ID variable. The second is a mode variable indicating whether this individual responded by telephone or by web. And the third is the sum score from this battery of mental health questions, taking a value on a continuous scale. So first of all, we would develop an imputation model for the sum score using only the data from the web respondents. So here our reference mode. So we would bring in some information on variables that we think would help us better predict the values of this variable, the sum score variable that we're interested in imputing. So for example, here we've added some additional columns to the data set on the slide relating to gender, social class, health, education, and cognitive ability. But these are just examples. You could add many variables here. So this imputation model is developed just amongst the web respondents, so only using information on how the sum score and these other variables co-vary amongst those responding by web. The sum scores for those individuals who in fact responded by telephone are artificially set to be missing. And then we apply our predictive model, our imputation model, using the data on gender, social class, health, education, cognitive ability that we've observed for our telephone respondents to impute the counterfactual sum score value. So this then represents our best guess, let's say, of what we would have observed for those individuals had they instead been observed via web. As I say, we do this multiple times, so we impute multiple data sets, each likely to have somewhat different values imputed for the sum score variable for our telephone respondents. We analyze each of those imputed data sets using the substantive model of interest, so estimating our descriptive statistics, associations, or causal effects that we're interested in, and pool these using standard rules to obtain appropriate standard errors. So, as I say, these are very standard methods in kind of applied research, but here we're using them for a slightly different purpose. So some key advantages and disadvantages of using this multiple imputation approach. As I've already said, this is increasingly commonly used, so it may already be familiar to many researchers, and there's easy to use functionality in the major statistical software. It's straightforward to implement for a wide variety of variable types. So here we were looking at the sum score, which we considered as a continuous variable. So your imputation model might be a linear regression model, which would allow us to model that on a continuous scale. But if instead you had a variable that was binary or unordered or ordered categorical or account variable, then it's very easy to use appropriate models to account for that within multiple imputation. Because this is a method that was devised for dealing with missing data, then of course we can combine it. We can handle mode effects and missing data within the same analysis in quite a seamless way. A major disadvantage here is that this approach is potentially very wasteful. So it's not using information on the variables that are subject to mode effects from those individuals who were observed in the alternate mode. So if I just skip back a few slides to this one here, when we're developing our imputation model, it's only done amongst the web respondents. So it's using information on all of these variables amongst the web respondents only. When we apply that to our telephone respondents, it's only using their observed information on gender, social class, health, education, and cognitive ability. We've just thrown away the information on their sum score. We essentially may as well not have observed that at all because it's not used in any way. So this is potentially wasteful, but also inefficient from a statistical perspective. And I haven't really talked about the assumption underlying multiple imputation. So in a missing data setting, this is the missing at random assumption that people may have heard. And what this means in the context of handling mode effects is that conditional on the variables that we use in our imputation model, answering in the alternate mode is not informative about the variable of the values to be imputed. And really, this is just equivalent to requiring that mode selection is correctly accounted for, which I think we've already emphasized is quite a difficult undertaking to guarantee that we've done, particularly when, thinking about the predictors of mode selection is something that's outside of the applied researchers' traditional interests, I guess. You think about the variables that you would want to include to account for confounding, which may or may not overlap with these variables to a certain extent, but this is really a different type of variable that needs to be included in the analysis, so requires careful thought and a different type of background knowledge. And I'll hand over to Liam. Thank you.
Great. Okay. So Richard's talked about two methods that are the more standard proposed methods, which have their flaws. Now I'm going to talk about quantitative bias analysis as a different approach to try and account for bias from mixed mode data. So what is quantitative bias analysis, or QBA? Well, it's not just one method. It's really a collection of methods that are designed to incorporate or output quantitative information on the sensitivity of an analysis, of an estimate rather, to bias. So the clue is in the name. You are using or obtaining quantitative information on how important bias is in practice. As it's a collection of methods, they span a whole different set of aims and how information is inputted or outputted, but this can span applications where you just use information from summary statistics like regression coefficients. Given a regression coefficient, what sort of bias would be necessary to overturn a result, or you can, as we're going to see, use QBA methods that amend record level data observations in your data set to account for bias. These might provide bounds on bias, how much bias is necessary to explain an association, or allow you to say, given a level of assumed bias, what is the corrected estimate that I would have identified if that bias wasn't there. They can also be used for any number of biases, so information, which is measurement error type biases, confounding and selection biases, and they can also be combined together as well, which is a nice feature of them. I've just added a few references at the end that you might be interested in reading afterwards. I'm going to talk about two QBA methods that can be applicable to mixed mode survey data. And the first one is relatively straightforward, and that's counterfactual simulation. And the basic idea here is just to correct the observed data for an assumed mode effect. So here we're going to use this counterfactual simulation to remove a mode effect in a continuous measure of quality of life, which is the CASP-6 measure that we've been seeing earlier in this presentation. So on screen, I've got a table which shows 6 rows of data. And this is a mixed mode survey. There's a column for mode where people responded via telephone or web. There's data on CASP-6, the quality of life, and degree, which is a binary variable. Now we assume that because it's a sensitive question, your quality of life, that people in the telephone mode might have reported higher quality of life than is actually the case in practice. So very simply with counterfactual simulation, we're just going to create another column of data in our data set, which I'm going to call sim. And then for people in the web mode, which we're going to treat as our reference mode, we're just going to use the observed CASP-6 value for those individuals. So we've got 5, 7, and 6 respectively. For the people in the telephone mode, we instead use a simulated value. And this is simply the observed CASP-6 measure. So for instance, in the first row, that would be the value of 4 minus an assumed mode effect. And I said before that there's lots of mode effect experiments that have been conducted. So we can imagine that there's a mode effect experiment that's been carried out comparing telephone and web modes in a similar population to what we're interested in this data set, and found an average mode effect of, say, 1 point. So in the telephone mode, you'd expect, due to the differences in item measurement, that people would give a 1 point higher average CASP-6 score on average. So yeah, you could just simply remove that, subtract that from the observed value, and then in the forward analyses, you just use that simulated column of data instead of the observed one. So what are we actually doing when we're doing this counterfactual simulation? Well, on screen, I've got a DAG, which shows let's say we're interested in the association between financial security and quality of life. These are both measured with a mode effect, and they might also be related to mode selection. So if we conditioned upon mode, we would remove the bias from the mode effect, but we would induce a collider bias due to mode selection. All we're simply doing, rather than using a conditioning strategy to account for mode, which would lead to collider bias. We're just using counterfactual simulation to remove those arrows from mode to the variable that we use. So we're removing the association due to mode effect with the simulated variables on the assumption that that's correct. So there's a number of advantages to this approach. One is that unlike MI, multiple imputation, we're actually using the information that's available. For people in the web mode, we use their observed information. For people in the telephone mode, we use their observed information, but just minus an assumed mode effect. It also didn't require any assumption about mode selection. So all we've done is make an assumption about mode effect, and that might be a reasonable assumption that we can have some confidence in because there's a relevant mode effects experiment that's been conducted already. There's also a lot of experimental evidence that we can use to say what a mode effect might be in practice. So here I've got the reference to the systematic review led by Georgia. Again, this, excuse me, reviewed 90 studies, and one thing that Georgia's also helpfully created is an online database which just gives the item level information for 4,000 different results from the 90 different studies, and you can use these to decide to find a set or at least one mode effect estimate that might be relevant to your particular counterfactual simulation that you want to do. Another approach is if you can't say with confidence what a mode effect might be in practice, plausibly, you could say what an implausible assumption would be instead. So just going back to the headline findings that I spoke about at the top of the presentation, mode effects rarely exceed something like 0.2 or 0.3 SD on average. So you could assume that a mode effect for this counterfactual simulation was one standard deviation, knowing that realistically that's not going to be how large it was in practice. If your substantive conclusion doesn't change, then that would be evidence, good evidence that your results are robust to mode effects. So even though you're not getting a precise and accurate unbiased estimate, you're at least being able to rule out mode effects as a particular problem for your analysis. So on screen, I've just got a simple example. This is an analysis of age 55 data from the National Child Development Study, which is the 1958 British birth cohort study. The interesting thing about the age 55 sweep was that it embedded a mode effects experiment. So it compared people in the telephone mode with a web mode. And we use this data just to look at the association between whether someone was in a professional occupation and their quality of life. Quality of life might, as measured by the CASP-6 score, might be subject to a mode effect for the reasons that we spoke about previously, and also professional social class, which might be not subject to a mode effect, but might be related to mode selection, creating a bias between those two variables. So this graph on screen just shows different regression estimates from different regressions. So on the most left-hand point, we have the naive estimate, which is basically just using the observed data. We can also use the experiment to unbiasedly estimate the mode effect and identify what the true association is between those two variables when accounting for survey design, and that gives us a stronger association than the naive estimate did. There's also, excuse me, the results of the approaches that Richard spoke about before, so adding a mode indicator to the regression model using multiple imputation and adding statistical control, so not just the mode indicator, but more control variables too. And these also change the estimate, some towards the unbiased experimental estimate, but they don't remove the bias exactly. And also these have the problem that they rely on assumptions that you can't verify in practice and might be implausible. On the right-hand side of the plot are different counterfactual simulations. So NOR-SD is just where we've taken the data as observed and rerun the analysis. So that's why it's the same as naive. And we know that's unlikely to be correct in practice because we think CASP-6 scores are biased by mode effects. After going from left to right, we're now increasingly adding extra mode effects in our counterfactual simulation. So the second point is 0.2 SD, and this is a reasonable assumption to make given other mode effects experiments that are have already been conducted. And in fact, in the NCDS experiment itself, the mode effect was about 0.2 SD. So when we do this counterfactual simulation with a 0.2 SD mode effect as our assumption, we get a reasonably very close estimate to when we properly use the experimental data. But even if we add increasing levels of measurement error into the mode effect, assume larger and larger mode effects, we still see the same qualitative result, which is that the two variables, professional social class and CASP-6 scores, are biased. We might not be identifying an unbiased causal effect, or sorry, an unbiased association, but in terms of the substantive qualitative conclusion that we might draw from that, it's the same. So we can say it's unlikely that mode effects are explaining the association that we've seen in this data. Now, a problem with this approach is that it doesn't work easily for non-continuous variables. So for continuous variables, we can just minus the average and we'll still get something on the same scale as the variable that we had already. But for things like binary variables, we can't minus 10% and have a variable that makes sense in practice. For binary variables, particularly, what you need is something like, depending on the setting, something like a negative predictive value, sensitivity value, or positive predictive value. And some of these can require assumptions about the underlying prevalence of the phenomena that you're interested in. And what this basically boils down to is an assumption about mode selection. So it doesn't have, for binary variables, it might not have the advantage that you had for this counterfactual simulation approach that you did have for the continuous variables. But you could still assume implausible values for the negative predictive value, so you can see if the results change substantively when making implausible assumptions. So there's still a possibility there. And then another QBA approach is something called simple sensitivity analysis. And there's a paper by Van der Wiel and Lee where they look at this for differential measurement error in binary variables. And that's what I want to talk about now. So in their setting, which isn't to do with mode effects specifically, they're interested in whether the association between two binary variables, x and y, can be explained by differential measurement error. So assuming that y, the outcome variable, is mismeasured, and that the degree of mismeasurement is related to the level of x, the exposure. So there's two paths through which those variables can be associated. There's the causal path from x to y star, or the path that you're interested in, I should say more specifically. And then there's the sort of spurious survey design-led path, which is from x to y. Based on a DAG like this, Van der Wiel and Lee are able to conclude that if you have a positive association in a risk ratio above 1 between the exposure x and the measured variable y star, that to explain this association entirely, that observed risk ratio must be less than the ratio of sensitivities according to x and levels of x, or the ratio of false positive probabilities. Now, our setting's slightly different because we're also saying that x might be a cause of differential measurement error. However, this is due to mode selection. So it's mode itself that is the cause of measurement error. That is the mode effect. But there is differential measurement error because x is a cause of mode selection, and then this goes on to have a mode effect. So we can note that the sensitivity of the measurement of y according to levels of x, it would then be a function of the sensitivity according to levels of m and the probability that someone is in a given mode given a level of x. And this is some intermediary value between the sensitivity given m equals 0 or m equals 1. I'm just talking about this at a high level, but we can apply this in some data. So here's an analysis of next steps, the cohort study run by a department, and the association between whether someone was female and their reported depression at age 32. So if you just take the data as is, you'll see that females have a 57 percent higher risk of reported depression. However, this depression was measured in a mixed mode survey, and there are differences in whether someone was the mode that someone used according to whether they were male or female. So women were more likely to appear in the web mode, and based on prior evidence, we might expect that people in the web mode versus this is relative to face-to-face or telephone, I think, that they might be more likely to report depression as well, because that's sensitive information. So we can take the information on the prevalence of being in the web mode according to being male or female, and we can use the results of a mode effect experiment. So here I'm just using the results of a mode effect experiment from that. This is actually the age 55 NCDS experiment to convert these into sensitivities. So we can assume that, say, all people with depression in the web will report having depression, whereas in the telephone, using the results of this Goodman study, we'll say that 81% of those people with depression will report that in the telephone survey. So plugging that into some of the equations that I showed you before, what you get is a ratio of sensitivities of something like 1.01. So this is far less than the observed risk ratio between depression as measured and female. And so the mode effect is not sufficient to explain the result. And in fact, it explains very little bias, if anything. We can also assume an implausible mode effect in this setup as well. So rather than take a mode effect estimate from a mode effects experiment, we could just assume that no one in the telephone survey whatsoever would report depression if they had it. And plugging that information into the same equations, what you'll see is that the ratio of sensitivities based between female and male, based on just simply due to mode selection, would only be 1.09. So again, this is far below the association observed between measured depression and sex. So again, even if we assume a very implausible mode effect, it's never going to be the case that no one in the telephone mode who's got depression doesn't report depression. We still wouldn't have enough measurement error. The mode effect wouldn't be large enough to explain the result that we see. Okay, so advantages. One of the advantages, particularly for counterfactual simulation, is that a detailed understanding of mode selection might not be required. This is difficult in practice. It's hard to create an experiment where you could work out what has a causal effect on mode selection. And again, it's probably outside people's area of expertise. They might be using survey data for another purpose rather than being interested in survey designs in and of themselves. It also uses the available information that you have, unlike multiple imputation, and it's extremely flexible. So in our counterfactual simulations, we could have assumed heterogeneity in the mode effect. We could have said mode effects were larger for females than males, for instance. We could also have different types of errors as well, like multiplicative ones as well, rather than additive ones as assumed before. QBA approaches, there's many of them and they can often be combined, so we can account for mode effects with the QBA approach alongside other biases at the same time. And a nice feature of simple sensitivity analysis is that it can be performed post hoc. So there are a lot of data analyses, published work out there already that have used mixed mode survey data, and we can't go back and do this record level counterfactual simulation, but we can at least do something to look at the regression coefficients that have been published to check whether mode effects are likely to explain the results. Some disadvantages are that we might not know a plausible mode effect for a given situation, though there's lots of mode effect experiments that have been conducted. It might not be conducted in the particular population that you're interested in for the particular variable that you're interested in. So we might not be able to rule in a particular plausible mode effect, but we can at least rule out implausible ones. So although we might not be able to find a plausible mode effect, we might be able to say what an implausible mode effect is, given those high-level findings from George's systematic review. And the other disadvantage is that for some of these methods, there's usually not any out-of-the-box functionality, so it requires some coding skills. I just wanted to end with 2 slides sort of meditating on, it overlaps with a point that someone said before about, does this matter in practice? And from the QBA sort of setup, we can, I think it helps to make explicit that the bias due to mode effects is dependent on a number of factors, and that these are all empirical things rather than theoretical things too. So one of them is that the relative bias really depends on what the association between X and Y would be absent the mixed mode. If there's no association between X and Y in a single mode, because absent using mixed mode survey data. So if you didn't have a mixed mode survey, there wouldn't be any association at all. Then the mixed mode survey design could cause substantive issues, because that would be the only reason for an association to exist. But if you've got a particularly strong association, like we did before with depression and female, then the mixed mode design might not be able to explain much of that in a relative sense. It also depends on the extent of the mode effect. So the fact that there's arrows going from mode to Y star or other measured variables in our data. And as we spoke before, this varies by variable, and overall you generally don't see anything exceeding something like 0.3 standard deviations. And again, that's going to limit what the bias can be as a result. It also depends on the strength of mode selection in practice. So this is the degree of imbalance across modes in the characteristics of individuals. And this is particularly related to the prevalence of the alternative mode. So in a lot of sequential mixed mode designs, what you might see is something like 80 to 90% of individuals are in the reference mode. So in the most recent sweep of Millennium Cohort Study, I think it's something like 89% of people respond by web and only about 11% respond by face-to-face. And obviously, given that few people actually respond in the alternate mode, that can't cause a huge amount of bias. Whereas if there's a more even split, if it was 50-50, then the bias might be worse. So just to reiterate, these are all empirical questions. Okay, so I've not worked out exactly what's the best way to present this analysis, but this is some ongoing work with Georgia and Richard, where we have a mode effects experiment and we've applied the results from that to the latest sweep of next steps to do some counterfactual simulations. So we've taken lots of different pairs of variables from the next steps data, and we've just looked at the association between the two. So this is presented as a specification curve, which basically just rank orders different associations between variables according to effect size. So at the left-hand side, we've got no association whatsoever, to the right-hand side, the largest effect estimate, which is something like 0.7 standard deviations. We've done that with the observed data, and then we've run the counterfactual simulation process and then re-estimated those associations. So the grey line shows those observed, the results that you get when you look at the observed data, and then the bars that go from this line are at the top of the bar or the bottom of the bar, away from the grey line, would be the estimate when you use counterfactual simulation. And the basic headline result from this is that the associations are very rarely moved, and when they are moved, not very rarely, they're rarely moved strongly away from the observed association that is there already. So at least in this data set, there doesn't appear to be much bias from mixed mode survey data. However, that comes with the caveats that I mentioned before. It's sequential mixed mode survey data with few people in the alternate mode, and it depends on the particular analysis that you are interested in. So there might be some variables that are more subject to mode selection and mode effects than others, but just something to think about. Okay, so I'm going to end it there, and we'll just go back to the Q&A. Thank you.